Dear students, in this video lecture, we will continue the 5.1 self-learning topic, periodic analog signals. Okay. So it is continuation of the periodic analog signal. So again, the course outcome of this lecture is you can understand the periodic analog signal and you can sketch the periodic and non-periodic analog signal, and also you are able to calculate what is phase of the signal, what is bandwidth of the signal, what is the frequency of the signal. Okay. So previously we had discussed what is frequency, what is period, and how we can calculate the frequency and how to sketch the periodic analog signals. Okay. So now we are going to discuss about phase. So what is phase? The term phase or phase shift can say that once again. The term phase or phase shift, we can say both are same. Phase or phase shift describe the position of the waveform relative to time zero. Okay, so we know that this is the time, this is the amplitude. So waveform, how it is starting? Okay, position of the waveform. So this position, how it is? Okay, so I already told this is zero, time zero. This is the time zero. How the waveforms are there? Accordingly, we can say the phase. If we think of the wave as something that can be shifted backward or forward along the time axis, phase describes the amount of that shift. Okay, so see here, it indicates status of the first cycle. So this waveform, first cycle, how it is started, it is based on the first cycle only. It is not represent to others. Why? Because the phase is relative to time zero. Time zero, how the waveforms are there. So the phase is measured in degrees or radians. Okay. So 0 degree, 90 degree or something, some degrees. We can say degree or in radian. Okay. So if example 360 degree is equivalent to 2 by radian. Okay. So here you can see I given clearly. It is 1 degree means, what is the 1 degree? 1 degree means 2 by 360 radians. Okay. Clear? In case 1 radian, what it will there? Yes, here. So 360 by 2 by, so that is degrees. 1 radian equal to 360 degree by 2 by. So here you see a phase shift is 360 degree corresponds to a shift of the complete period. 0 degree, 90 degree, then 180 degree, 270 degree and 360 degree. Okay. So once if it is reached the 360 degree, we can say that is a complete period. Okay. So here 180 degree corresponds to shift of the 1/2 of a period. So this only will be considered as half period. Okay. So up to this point. Then 90 degrees corresponds to the quarter period. Okay. This is the up to this only. The signal will be up to this point. This is the 90 degree. Okay. So this is 90 degree. This is 180 degree. This 360 degree. This 270 degree. So clearly say the first period. Okay, so first the waveform starting with time 0, start with the 0 degree, then the degree is 0. Okay, so then second one you see that half time phase. Okay, so I already told this is the 90 degree. Okay, so it will reach when time 0, the signal start with 90 degree. So that means the degree of the signal is 90 degree. Here the half is over already. We start from next to half. So the degree is half of the time. Maybe What is the degree? 270 degree. Sorry, 180 degree. Sorry, 180 degree. Okay, so that we are clearly mentioned. So we already seen this diagram. Diagram is showing that zero amplitude and then 90 degree with peak amplitude. So what they are saying that the sine wave with phase zero. If it is phase zero means what it will do? It is a zero amplitude time and wave also starting with that same period. It is zero amplitude means what will be there? Zero means it will be increasing. Okay, that they are mentioned. The phase is 90. So in case already it is reached. Okay, phase is in time 0 it is 90. What it will do? Then again it will be going to reduce. Okay, so it is decreasing. If degree is 180, so already the period is over, half period, then will again going to reduce, decreasing. Okay, here also decreasing. So you just remember according to the phase only, the wave will be start in the time 0 point. Another way to look the phase is terms of shift or offset. How we can say that? If phase is 0 degree, it is not shifted. Okay. If the phase is 90 degree, shifted to the left by cycle. Okay. However, note that the signal does not really exist before time 0. So in case 180 degree shifted, the left by cycle. However, note that signal does not really exist before time 0. Okay. So what they are saying that even if 90 degree or 180 degree or 0 degree, so the signal will be shifted or not, it will be identified. See here, a sine wave is offset of 1 by 6 cycles. Okay, 1 by 6 cycles with respect to time 0. Okay, with respect to time 0. And is its phase in degree and radians. So what we have to do? The periods will start with 1 by 6 cycles. So 1 by 6 into 360 because we are converted into the degrees. So what is the degree? So 60 degree. So the degree of the phase is 60 degree. So what is the radian? So already we have identified the radian. What is the degree? What is the radian? So how to convert the radian? 1 equal to 2 by 360. This is the formula we know, 1 radian. So 60 degree means, sorry. Oh, so 1 degree equal to 2 by 360 degree. So total 60 means 60 into 2 by 360. So what is the value it will come? 6 by 3 equal to by 3 radians. Okay. So 1 radian equal to this value. So 60 degree means 60 radians will be calculated. 5 by 3 radian values. 5 by 3 values, what is the value? 1.046. Okay. So normally 1.046 radian. So this is the calculation. So now we are going to discuss about wavelength. Wavelength is another characteristics of the signal traveling through the transmission medium. So what is the wavelength? Wavelength binds period or frequency of a simple sine wave to the propagation speed of the medium. Okay, so see this diagram. This is the transmission medium at time t, here at time t plus t. So how much time it is taking in the direction of propagation? Okay, so the wave it take how much length it is taking. It is the wavelength of the signal. Wavelength is propagation speed into period. Okay, so the formula equal to propagation speed into period. The period equal to 1 by frequency. Then we can say that propagation speed by frequency. Okay, so here we are using lambda equal to C by F. So F is the frequency values and propagation propagation speed is C. So the wavelength lambda equal to C by F. So now you just listen here. The propagation speed of electromagnetic signals depends on the medium and on the frequency of the signals. Okay, so how much speed it is going, how we can say that it is according to the electromagnetic signals transmitted according to the medium and also frequency of the medium. So here, so normally we know that the light is propagated with the speed of 3 into 10 power 8 milliseconds. That speed is lower in air and even lower in cable. Okay. So if air if you are calculated, it is okay. Then even if you will go in the lower, it is sorry in cable again it will be decreased. The wavelength is normally measured in micrometers. That we can say that microns instead of meters. Okay. So see here the wavelength of the red lights. For example, we can say the frequency equal to 4 into 10 power 14 in air. And normally frequency value is this. The propagation speed is 3 into 10 power 8. So when we are calculating this, we will get the 0.75 micrometers. That is microns. The time and frequency domain. A sine wave is comprehensively defined by its amplitude, frequency, and phase. Already we know that. So the sine wave is amplitude, time, and then frequency. This depends on like that. We have been showing a sine wave by using what is called time domain plot. If you are drawing this diagram, it is time domain plot. Okay. Phase is not explicitly shown on the time domain plot. So here, phase we cannot be able to say in the time domain, but we can say that in frequency domain. To show the relationship between amplitude and the frequency, we can use what is called frequency domain plot. How we can draw the frequency domain plot? Frequency domain plot means it is concerned with only the peak value and the frequency. Okay. What is the peak value of frequency? The waveform. That will be according to that it will be drawn. Changes of the amplitude during one period. So example, if the already we know that this is the waveform is taking this much speed. So example, what is the peak value? For example, 5 volt. Okay. So here, what is the frequency? How many cycles are completed in 1 second? So example, if 5 cycles are completed means 5. The frequency is 5 hertz. Okay. So what is the voltage? 5 voltage. So how we can draw with the frequency? Frequency equal to, for example, 5 hertz. So here 5f is there, 1f, 2f, 3f like that it will go 5f. We can draw up to 5 volt. Okay, so this may be the 5 volt. So simply we can draw the line in this is the frequency level. So this is the frequency domain plot. Okay. So see here the clear explanation is there. Peak value is 5. It is common to all the wave. And then frequency of this entire wave is 6 hertz. So 6 frequency will take the 5 volt. Okay, this is the frequency domain plot. This is the time domain plot. Okay, we just remind it how to draw. A complete sine wave is in the time domain can be represented as one single spike of the frequency domain. Okay. So this simple examples here they are given. So here frequency there is no changes in the signals 15 volt. Okay. So what is the frequency value? Frequency is 0 because the waves are straight. There is no alterations. So then the 15 volt. So here the frequency value is 0. Then 15 it is mentioned. The second wave, pink color wave, the peak amplitude is 8. Okay, so here it is mentioned that how many peak values are there, how many, what is the wavelength, like sorry, frequency. So up to this point 1, sorry, here 1, 2, 3, 4, 5, 6, 7 and 8. Okay, so ping value 8, amplitude is 10. Okay, so 8 frequency, green color have 16. So there is a 16 periods are there here. Okay, so we can represent time domain like this. Dear students, now I am stopping this video presentation now, and I will continue this lecture in next video 5.3. Please watch this video, and we will continue in the next video.